Welcome, everyone. Thank you for being here. It's my pleasure to introduce the 8th edition of the deLIGHTed Talks, which is about good light and good sleep. So I'll thank the Good Light Group and the partner, the Daylight Academy, Luger Research, the International Association of Lighting Designer, and the Society for Light, Rhythm, and Circadian Health to organize this great talk. What we will do today first, so I'll introduce myself and do a small introduction about why is light so important for the circadian rhythm. And then we'll have Dr. Renske and Dr. Jeffrey Hubbard, who will give a talk, and I'll introduce them a little bit later. So first of all, why is light important? As well, sorry, before I start, you will see the Q&R logo on your screen. So we'll take all the questions at the end of all the presentation. So please write down all the questions you have in the Q&R, and we will read them in the end. Okay, so why is light important? As you all know, we live on Earth, and Earth is rotating at a 24-hour cycle. So we are supposed to live according to the light and dark cycle, which is called the circadian rhythm. So it's a rhythm about approximately 24 hours. How does that work? In our brain, we have a biological clock, which is in the suprachiasmatic nucleus right here. And this clock will give the rhythm to our body. But this clock, if you don't give any what we call zeitgeber, so external time giver, it will not run at 24 hours specifically. So what we need to do is to give this clock an external output to give to know what time it is. So every morning, when you see the light, your biological clock will be reset, meaning that when it's reset, it will give information through different pathways, and the pineal gland will synthesize melatonin. Melatonin is inhibited with the presence of light and activate when darkness is there. So when your body sees melatonin, we know that it's nighttime, and when there is light, there is no melatonin at all. And we'll talk a little bit about melatonin later. And all these pathways go through a specific cells in our retina. These cells, they are called the retinal ganglion cells, and they go through, or the light through these cells is called the non-visual pathway. So the non-visual pathway is all the effects of light that doesn't impact vision. We have rods and cones for the visual structures, and these specific cells that are sensitive to a specific wavelength, which is 480 nanometers, so the blue wavelength. So every time these blue wavelengths are caught by these retinal ganglion cells, it will send a message to the suprachiasmatic nucleus and then produce or stop melatonin. Through this pathway, the non-visual brain area, in blue here, you can see it here, it will either activate the sleep-promoting neurons or the wake-promoting neurons through direct or indirect pathway, and this you will see a bit later as well. So why is it important? Can we live without lights? There is some experiment that has been done in the 60s. It's Michel Stiff. He decided to spend some days in a cave without any daylight. And what he did, he tells his team when he went to bed and when he wake up. And the team just puts a line here to see when he was sleeping. What we saw after some 60 days is that every day he was going to bed a bit later and waking up a bit later. And this is how we realize that our biological clock is not at a 24-hour cycle. And without light, we cannot really reset the clock. And we just, as we call it, like we are in free running. So we are just delayed every day a little bit more. There is another study for, if you were at another talk a month ago that I presented, it's in 2021. There was 14 people living in a cave, again, without any day and night cycle. And we try to see if there is any synchronization between all these people and if they live on a 24-hour cycle. Just a quick graph to show you. Here in white, that means that all the people are asleep. And in dark, when all the people are awake. Here it's before entering the cave, you see that they all sleep during the night and they are awake during the day. So they are still living on a 24-hour cycle. In the cave, you can see here the same as Michel's chiffre. So every day they were going to bed a little bit later and wake up a little bit later for the first week. And then after that, there is no synchronization at all. Everyone was going to bed when they fell asleep and wake up when they were rested, but no one did that at the same time. So there was no synchronization with them. And as soon as they get out of the cave, with the light, they get synchronized again, where everyone was sleeping during the night, during the night and awake during the day. And you can see it here, outside the cave, so before and when they came out of the cave, they had a cycle of 24-hour.09. And inside the cave, the mean cycle was 31.6. So here you can really see that without light, we can't really live on a 24-hour cycle, and we still need light. We still have a cycle, but we still need light to live on a 24-hour cycle. And why is that so important? So we see our biological clock here, and we have our peripheral clocks. Every time that the central clock is reset with the light, it gives the information to our body to synchronize our body. And that's the synchronization between our internal circadian rhythm and the external time giver. As I said before, when this central clock is reset, we also have this melatonin. So melatonin will increase at night to make you fall asleep, maintain you asleep. And in the morning, when you see the light, there's no melatonin anymore and you wake up. So it's really important here to have a little bit of light in the evening so that melatonin can increase, and a lot of light in the morning so that melatonin stops and we reset our internal clock. So this is important for the natural lights, but we'll see, Renske will explain it as well. With artificial lights, it can also impact how the body sees the light and how the body reacts depending on our 24-hour cycle. If we don't listen to our body, meaning that when we have all the sleep signal and we don't go to bed, or we don't wake up at the time when we are rested, then that's how we have some sleep problems. Or so because we don't listen to our body nowadays, we have a lot of different activities, work or family and so on, and we don't really listen to our body, and that's how it will impact our behavior and our physiology. So now I will introduce Renske that will talk a little bit more about all these effects. Sorry, so it's my pleasure to introduce Dr. Renske Locke. She's the Vice President of the Society of Light, Rhythm and Circadian Health. She earned her PhD at the University of Groningen, and she is now a senior postdoc at the Department of Psychology and Behavioral Science at Stanford. And she specializes in the non-image forming effect of light on circadian rhythm and sleep-wake pattern. And today she'll talk about how daytime light exposure shapes nighttime sleep quality. So, Renske, I give you the floor.
Thank you. There we go. Good morning, everybody. Very happy to be here. Thank you for the organizers for organizing this super interesting webinar, and I'm very happy to be presenting here. I'll be talking a little bit about some of the work that we did and give a small overview of the things that have been done in the field with respect to light exposure and how it can actually influence our sleep at night, which is usually a topic that people don't really think about. So the title of my talk is How Daytime Night Exposure Shapes Nighttime Sleep Quality. And something that I kind of want to bring to the attention is that I personally think that the emergence of electrical lighting has changed our relationship with lighting as it extends our ability to stay up beyond dusk. And the easiest way to think about this is that before there was any electrical lighting or any other way of making light after sunset, it was really as soon as the sun set, we would go to bed, and as soon as the sun rose, we would come up. So we would live as long as the sun is out, and we would go to bed as soon as the sun set. And of course, this relationship kind of changed first with the emergence of fire, then with the emergence of gas. And then as we progressed, we got incandescent light, fluorescent light, and now we're kind of in the era of LED lighting. And the fact that we have access to all these light tools makes it that we don't just have to go to bed as soon as the sun sets and actually have to wake up as soon as the sun rises. And, you know, saying it like this, it almost sounds a bit crazy. So it's something that we're really, really not used to anymore. But I think this ability to expose ourselves to artificial light has changed our relationship with lighting and our rest activity patterns and sleep patterns. And it's kind of funny because if you look at the original plaque of the Edison electrical light bulb, it says, do not attempt to light with match, simply turn the key on the wall by the door. And then in very small in the bottom, it says the use of electricity for light is in no way harmful to health, nor does it affect the soundness of our sleep. And this is something that I kind of want to attest. I think it was true for that time, that was our current line of thinking. But I think that has changed a lot. And we know that this is not actually true, and that light can definitely influence the soundness of sleep. And just like Virginie explained, I will reiterate very briefly, is that the fact that you can see me and that I can really not see you, but that I can see my presentation, is because light really enables us to perceive the world around us. So this is a depiction of the eye. Let me make this pointer. So this is a depiction of the eye where light enters the pupil and it hits this back layer of the eye, which is called the retina. And the retina is packed with cells that translate light information to the brain. And this is the reason why we can see, both when there's high intensity lighting and also in dusk and dawn. So light enables us to perceive the world around us. But light does so much more. So light has a lot of non-image forming effects of light, which means effects of light that have nothing to do with vision. And just like Virginie explained, it means that light can influence when we go to sleep, how we go to sleep, how alert we feel, and how well we perform cognitively, for example. And light has these functions through various pathways in the brain. And the most well-known pathway through the brain is the projection from all these cells in the eye to the SCN, the suprachiasmatic nucleus, the location of the central pacemaker. And this is a pathway that has been studied for, I think, at least 50 years, in which we know that light can influence the timing of the suprachiasmatic nucleus. But we start to know more and more that there are effects of light that go beyond the suprachiasmatic nucleus. So there are projections of all these cells in the eye to various nuclei in the brain, independent of the SCN. And these nuclei have been associated with lots of non-image forming functions, including sleep-wake regulation, which is located or organized in the ventrolateral preoptic nucleus. There are regions in the brain associated with mood, so light can have direct effects on how you feel, and alertness and cognition, which is mostly located in the lateral hypothalamus. And I think when I talk about light and the effects of light, I cannot really talk about it without talking about at least light intensity. So for the rest of the presentation, I will kind of reference various light intensities, and all that I really want you to remember is if I talk about 5 to 10 lux, I talk about very, very dim lighting, just enough to see, more or less an equivalent to being close to a candle. If I talk about 150 to 500 lux, that's usually office lighting or home living room lighting. And if I talk about lots of sunlight, so above 10,000 lux, I'm talking about outdoor light exposure and sunlight therapy lamps. And one of the most common questions I actually get is, do I also get 10,000 lux if I go outdoors and it's a cloudy day? And the short answer is yes. Even on cloudy days, you get above 10,000 lux of light if you go outdoors. So you can imagine the range is quite large. Candlelight, very dim. Home office lighting is usually a little bit in between, and outdoor light exposure is super intense and gives the strongest signals to our brain with respect to time of day and what to do, really. So today I'm going to talk a little bit about the light effects on physiology and sleep. And I'm going to do so because I personally think that light stands as one of the most powerful non-pharmacological tools available to really promote and enhance human health and well-being, and if we use it correctly. And it has really far-reaching effects on both our psychology, which I'm not going to be talking about today, but also our physiology. So the question then is, can daytime light exposure improve or change nighttime sleep? And I really want to preface that by saying that a lot of popular articles like to highlight the negative roles of light. And I think if you go on Google and Google light and health or light and sleep, these are the kinds of articles that you'll see, how artificial light at night really influences our quality of sleep, how it has effects on, for example, Alzheimer's progression or the development of Alzheimer's, how it's bad for health overall. And how it influences obesity, for example, and heart health. And I think, yeah, these articles kind of like to highlight the negative effects of light, but I think something that we kind of forget, and this is coming back to the beginning, is that light really influences our behavior. So being exposed to a lot of light at night usually changes our behavior. And this is kind of a famous tweet that Netflix put out in 2017 saying, "Sleep is my greatest enemy." And something that Netflix acknowledged is that its biggest competitors is not Amazon or Hulu or cable, but it's really sleep. And if you think about it, all that Netflix wants to do is make you, sit and watch the next episode in the evening. And of course, when you're doing this, you're not sitting in the dark, right? So you're being exposed to artificial lighting. So the big question then kind of becomes, is it really the light itself that has all these negative influences on human health? Or is it what light enables us to do? In other words, stay up and watch Netflix. And these are some of the questions that I will not completely go into today because a lot of this still remains to be done. But it's kind of to be a little bit provocative and make you think about these kind of things. So if we study these kinds of questions, light and human behavior and influences on health, we kind of have to turn to big population studies. So we like to assess sleep patterns in large-scale population studies. And we do so by using a wrist-worn device. It's called an ActiWatch, and you just place it around your wrist. And with that, we can record rest activity patterns in humans. And when we plot that out, this is kind of what it looks like. So this is the rest activity pattern of a participant on one day of the week, on Monday and Tuesday. And you'll see intervals where there's very little activity, very few black bars, meaning intervals for sleep. And there are intervals where people are very active. So lots of black bars means lots of activity. So these are periods where people are really awake. And you can measure this for every day of the week, and you can create something that is called an actogram, which very clearly outlines when somebody is asleep, very few black bars, very few activity, and when somebody is awake, lots of activity. And this in the lab or in research, we really do this with a research grade device. But it's no different than what the consumer wearables really do. So if anybody in the audience has an ActiWatch or a Fitbit or a Garmin, this is really what your watch does to tell you something about your timing of sleep and also about the quality of sleep. And we can use this data to inform us about the influence of these rest activity patterns on health. So if we look at the timing of sleep, for example, we can see how this affects our health. And if there is a relationship between the timing of sleep when we go to bed and how healthy we really are. And to do so, we looked into the data of the UK Biobank. And I don't know if anybody in the audience knows, but this is a really, really big biobank with millions of activity records. Each activity record spans 1 week of minute by minute data, and that means for one participant, you have about 10,000 data points. And you have over 1 million participants. So in the end, we had to analyze billions of data points to extract the sleep timing of about 74,000 individuals. And then we used ICD-10 codes, basically hospital codes. So you go to the hospital and you get diagnosed with a certain disorder to assess physical and mental health outcomes. And really with the question, does sleep timing influence your mental and physical health? And the short answer is it really does. So what we noticed in individuals that go to bed early or early-ish, I mean, these are people in the UK and their bedtimes are quite late, I would say, to begin with. So early people went to bed around 11:30. Late people went to bed around 2 a.m. And what we noticed is that there was a significant influence on their mental and physical health. And all you really need to know is if something is red, it means significantly worse. And if something is gray, it means non-significantly worse or better. And blue means significantly better. In other words, when they went to bed early, they had a little bit less chance of having depression. But when they went to bed late, there were much higher rates of mental, behavioral, and neurodevelopmental disorders, depression, and generalized anxiety disorder. In other words, those that go to bed late have a higher chance of having mental health disorders. And it's not just mental health disorders, it's actually also physical health disorders. So all the disorders that we investigated were higher in those that went to bed late. So metabolic disorders, diabetes, obesity, hypertension, circulatory disorders, digestive disorders, respiratory disorders, and even all-cause cancer. There were significantly higher rates of all these diseases in people that went to bed late versus people that went to bed early, meaning that sleep time at least was associated with both mental and physical health. Now, of course, an association is an association, so we were curious, can we determine this a little bit better? And something you can do is called a survival curve analysis. And it means that at time point 0, you grab all the people that never have had this disease before. So in this case, these were the levels of depression. So we investigated all the people that at time point 0 never have had depression before. And we looked if in the 8 years, so we looked up to 8 years later, if they ever developed depression. And if these rates were different for those that went to bed early in yellow or those that went to bed late in purple. And the rates were very, very different. So if we look at those who went to bed early, at the end of the 8-year follow-up mark, there were about 97.5% of the people that still did not develop depression. Whereas in those that went to bed late, there were many more that actually developed depression. And of course, you can say the percentages here are very small, it's a 1 to 2% change. But if you remember that this is in about 70 4,000 people, it means if you have a 1% difference, that means 700 people more develop depression that went to bed late versus that went to bed early. And also this was something that was mimicked in the other disorders that we investigated. So also in mental, behavioral, and neurodevelopmental disorders, depression, as I just showed you, generalized anxiety disorder, and some of the physical disorders that we included, including diabetes, obesity, respiratory disorder, hypertension, and circulatory disorder. We see the same pattern, such that people that go to bed late develop more of these mental and physical health disorders than people that go to bed early. In other words, timing of sleep has a significant influence on your mental and physiological health. And again, if this is due to the light, because the hypothesis is when you go to bed late, you're not sitting in the dark. We don't know that yet because this data set didn't lend itself to an analysis of light. So this is something that still remains to be determined. So of course, the title of my talk really is about sleep quality and lighting. So what is it about light that can be positive for human health and positive for sleep? Because if there's one thing that we do know is that good sleep is essential for mental and physical health. So then the question kind of becomes, can light influence how we sleep at night? And can light have these positive effects as well? So we did this quite interesting study in which we investigated the daytime light exposure effects on nighttime sleep quality in young, healthy adults. And what we really did is we included a bunch of young, healthy people, and we asked them to go outside and go for a walk for about 3 hours at a specific time in the day. And we asked them to do this once under normal light conditions, so high intensity lighting, being exposed to this 10,000 lux, and once under attenuated light, so dim light conditions. And if I talk about dim light conditions, what we really did is we asked them to do the exact same walk, but wearing really big ski goggles that reduce the light intensity up to 10 lux, so candlelight light intensity. And then we went into their houses and we put a bunch of electrodes on their face and we told them to go to sleep whenever they wanted and we would record their sleep. So we went to their house and attached electrodes to their skull and this is how they actually went to bed. And in the morning we asked them, how do you actually feel you slept? So we had both, let's say, an objective output measure of sleep, so electrodes, PSG, and we had a subjective measure of how they felt they slept. And we were very interested in how these two would correlate and if light could positively influence the sleep experience. And interestingly, if we look at these results, and in gray are depicted the ones in dim light, so with the big ski goggles, and in yellow are the ones under high intensity lighting, we saw that there were really no effects on self-chosen timing of sleep or sleep duration. In other words, independent of how much light they were exposed to, they actually went to bed at the same time and they slept equally long. And by the time that they went to bed, so that's the bottom graph, they actually felt equally sleepy. So we're always interested in how alert or how sleepy they felt. However, if we look at the outputs of the PSG, so the electrodes attached to the skull, we see that individuals, when they were exposed to the high intensity lighting, so without the ski goggles, they had a lot more deep sleep compared to when they were exposed to the dim lighting. So they slept a lot deeper, they were awake a lot less, and they had less light sleep. So their sleep was more intense and more consolidated, really. And interestingly, what we also saw is the next morning, they felt a lot better when they woke up. So both they slept deeper and the next morning, if they had been exposed to high intensity lighting, they felt a lot more alert. So this is a sign that the amount of light exposure, so if you're exposed to a lot of light during the day, you'll sleep better. And the next day, you'll actually wake up feeling a lot more refreshed. So this is a really positive effect of light. And this was very exciting to us. But of course, we conducted this in healthy young individuals. And if there's one thing about healthy young individuals, they do not have any sleep problems. They always sleep good. So it's really amazing to find an improvement in sleep because it's kind of like cleaning a window that is already super clean. You cannot get that much improvement. So then we kind of asked whether there maybe would be a therapeutic applicability of light. So in other words, can we also improve sleep in those that have sleep problems by exposing them to more light? So then you kind of have to find a group that has sleep problems. And as I said, young individuals have perfect sleep. So they go to bed, they have a little bit of light sleep, they wake up a couple of times, and they have lots of deep sleep. But for those in the audience that maybe are a little bit older, know that your sleep changes with age. And as we grow older, something that becomes very apparent is that the periods of wakefulness really increase. So as opposed to really, having lots of light and deep sleep with a little bit of wakefulness when we're young, as we get older, we get many more bouts of wakefulness. Less deep sleep and a little bit less light sleep. So these are really people that we would qualify as having a little bit of sleep problems, because they will say it's very, very bothersome. And this is something that, again, we can quantify quite nicely with these ActiWatches, these wrist-borne devices. And if you plot out their rest activity data, this is more or less what it would look like. So if you have low sleep-wake fragmentation, so kind of what the young people have, you go to bed, you sleep, and during the day you're awake. This is kind of what it would look like. So you have lots of activity during the day, and by the time you go to bed, you have very little activity because you're asleep. However, as we age and we get more of the sleep-wake fragmentation, you'll see that the pattern becomes a bit more fragmented. As I indicated, while we are asleep, we get bouts of wakefulness. So we sleep a little, we're awake a little, we sleep some more, we're awake some more, and we sleep some more. And usually what this also means, and that's why I call it sleep-wake fragmentation, is that during the day, these are also the people that like to sleep or take some naps during the day because they don't sleep so much at night. So during the day, they're active for a little bit, then they snooze off a little bit, then they're active, they snooze. And, one of the most common scenarios is somebody sitting in front of the TV and like falling asleep for a little bit, and then being awake for a little bit, and then falling asleep again. And this is really a pattern of, we would qualify high sleep-wake fragmentation. And as I mentioned, it's very bothersome to the people themselves. I mean, people don't want to be asleep during the day. And it's also associated with lots of mental and physical health disorders and cognitive decline. So our idea is that if we can restore this sleep-wake fragmentation, maybe by light exposure, maybe we can also improve these mental and physical illnesses and restore the cognitive decline that usually goes with the sleep-wake fragmentation. And we have some exciting preliminary data showing that this might be the case. So it's preliminary, so not conclusatory. This is very much ongoing research, but I wanted to share with you today that we have some insights that light might help with sleep-wake fragmentation. So this is in a sample of about, I noted it here actually, we did this in a sample of 877 men that were a median age of 80 years. So they were quite old and they had quite some sleep-wake fragmentation as well. And we looked at their daytime light exposure profiles and how much sleep-wake fragmentation they had. And we noticed that in those that had very little sleep-wake fragmentation, so nice activity patterns during the day, very little activity at night, they spent a lot of time outdoors. So they were outdoors for about 2 hours a day. So they got a lot of light exposure, and this was associated with less sleep-wake fragmentation, better mental health, better physical health, and better cognitive health. On the other hand, those with lots of sleep-wake fragmentation, so lots of sleep during the day and lots of activity at night, they spend very, very little time outdoors, maybe, 0 to 30 minutes only, suggesting that the amount of outdoor light exposure is significantly associated, at least with the degree of sleep-wake fragmentation. And now the next step, of course, is to test this. So if we intervene and if we expose this group of people with lots of sleep-wake fragmentation to high intensity lighting at specific times of day, will they turn to better sleepers? And this is something that we're very interested in doing over the next couple of years. So today, my talk in how daytime light exposure shapes nighttime sleep quality. I hope I showed you that sleep timing is linked to both mental and physical health, with later sleep schedules associated with poorer mental and physical health outcomes. Exposure to daytime daylight exposure can improve sleep quality and reduce next day sleepiness, even in people who are already very good sleepers. And daytime light exposure is linked to improved sleep-wake consolidation in older adults who often experience a greater degree of sleep-wake fragmentation and various mental and physical health disorders. So with that, I would really like to thank the organizing committee again for providing me the opportunity to present my work here today. And my supervisors, my current supervisor, Jamie Seitzer at Stanford University, my previous supervisors at the University of Groningen, Domien Beersma and Roelof Hut, and from Chrono at Work, Marijke Gordijn. Thank you so much for listening.
Thank you very much, Renske, for this very interesting talk. If you have any question in the audience, don't hesitate to put them in the Q&A and we'll answer them after Jeffrey's talk. So now it's my pleasure to introduce Dr. Jeffrey Hubbard. He earned his PhD in fundamental neuroscience in sleep neurophysiology at the University of Strasbourg. And he's now a translational researcher specialized in the regulatory mechanisms of sleep and waking behavior and clinical sleep disorder. And today he'll talk about the opposing forces of light and darkness on sleep and waking behavior, lessons from nocturnal and diurnal animals.
Thank you so much. Let me see if I can share this properly. Okay, we tested it earlier, so it should be okay. Can you hear me? Perfect. Okay. So thank you so much again to the committee for giving me this opportunity to talk. So as Virginie said, I have spent my research career kind of looking at different species across from small little rodents, which I'll talk about today, all the way up to clinical sleep disorders. So what I wanted to do today is to take a few steps back down the staircase of evolution to these smaller animals to give you an idea of what we use these animals for in laboratory research to better understand kind of the fundamental processes of how light is interpreted by the brain and how this affects sleep and waking behavior. So today I'm going to talk specifically, I want to talk about the direct effect of light, and I'll tell you what I mean by this. Renske already mentioned this a bit. And then how can we isolate this direct effect in laboratory mice? So in a controlled setting, what would we then observe in diurnal rodents as a consequence? So just very briefly, how sleep and waking are kind of thought to be regulated, at least at this point, is we think about these two processes of their circadian and homeostasis. So the circadian process is this idea of gating sleep and waking based on a temporal niche for the animal, so that some animals are more day active, some animals are more day active, some are more night active, some are somewhere in between. Of course, behavior can override this, as we know from sleeping during the day or staying up the entire night. As both of the previous speakers said, this is controlled by the central clock and the hypothalamus, the suprachiasmatic nucleus. We have also this other process called the homeostatic process. This is very broadly speaking, it keeps track of sleep propensity. It's an idea represented by an hourglass there. It can be reflected in low frequency brain activity during sleep and other physiological signals. But I would also like today to talk about something called the direct, let's say the direct effect of light, or a non-circadian process. You can think of this as a bit like a flashlight at night. So obviously the pupillary reflex is a very common thing that everyone has noticed. If you go to a bright area, your pupil will constrict. Vice versa, if you're in a dark area, it will slowly expand to allow more light in. This is important for melatonin suppression as well, which Virginie mentioned. We do also know that, and I will discuss this today, it can be also affect acute induction of sleep and waking phases. So of course, again, if you shine a flashlight in somebody's eyes while they're sleeping, they will wake up to a certain extent. And this idea is supported by studies not only in model organisms like rodents, but also in human research and clinical studies as well. So how is light interpreted by the brain? I know we've already discussed this twice today, but just to give you an idea, again, what I'm going to discuss, so this non-image and image-forming cells that Renske mentioned, and Virginie are located, and let me just turn on my laser pointer, located in these melanopsin or OPN4 intrinsically photosensitive retinal ganglion cells. We also know that rods and cones are important for this, although to a much less strong extent, they're more indicated for image forming. The melanopsin cells themselves in the retina, they project to a lot of parts of the brain. Here's just a very few examples. One, the superior colliculus, so very important for light information to pass to areas of the brain involved in orientation, but also to the hypothalamus to control our eating behavior, and then also sleep and waking. So why do we use animal models? This is always a discussion, of course, in research. One of the reasons we do it is to have a completely controllable environment. So in terms of light, it would be about manipulating the amount of exposure the animal has, but also the intensity. If we want to do experiments where we shut light on and off, it's much easier to do this in a controlled environment. Of course, we can also measure things with the feeding behavior if we want to control the amount of food or the type of food that they get, how this influences their behaviors, we can do this. Second thing is that it allows us to do long-term physiological capture. So in the case of what I'll discuss today are multi-day recordings of sleep and wake behavior. The most obvious reason that we use this in a broader sense in biology and neuroscience is that we have the opportunity to add and remove genetic, we can use genetic tools to add or remove genes to the animals in order to see how they react. And today, for example, I'll discuss what happens when you remove the gene that encodes for melanopsin. It also gives us evolutionary insight. So again, looking at these different temporal niches, why these animals evolved in a certain way and how this interacts us in their brain. I will give you a spoiler. For example, we still don't really know why some animals are nocturnal and diurnal because the light going into their eye is the same light. So we're still working on it. Hopefully in some years we'll figure this out, but we have some hypotheses, but we don't know yet. So also, finally, what's very important is the translational impact. There's very often discoveries that were made in animal models led to changes in sleep medicine and chronobiology, and even certain ideas about public health recommendations come from these original models. So we have talked multiple times now about melatonin. And it's very important, certainly when we talk about chronobiology, light exposure, circadian research. The problem with mice in the laboratory is the majority of them do not produce melatonin. This is because some mutations that exist in the most commonly used models that will modify melatonin synthesis, but also it's quite possible that animals which were naturally more geared towards breeding at certain times of the year under certain light dark conditions had mutations in melatonin production. So we kind of force the mutation into the animals. And then we do also have some strains which are used less optional for example, the CBA strain and the C3H strain of mouse, they do produce melatonin. Just to show you what this looks like. So the normal C57 Black 6 mouse, which is what is used in most cases, they have no melatonin production over the night. However, we talk about mice being nocturnal, but their melatonin peak is still during the night when they are active. So we also don't know what role melatonin plays in nocturnal animals versus what we presume the role it plays in human beings. So how do we measure sleep and waking in rodents? We use something very similar to what is done in humans that Renske mentioned, so with electrodes. However, because the mice won't sit still, we have to put the electrodes directly onto the animal. We record with a system that allows us to capture brain activity and muscle activity. So here we can see a waking signal, for example, very kind of high frequency moving around, a lot of movement here on the EMG. This is the muscle activity. When the animal goes into normal sleeping, we have much slower brain activity, not a lot of muscle movement. And then rapid eye movement sleep. So We don't know whether the animals are dreaming during the sleep, but in any case, they have an active brain, but a relatively suppressed muscle tone. So experimental evidence in in mice, for example, on the role of light and dark and sleep and waking, I just want to briefly make some points that mice in general, there are some mice that are more geared towards diurnal behavior, but in general, mice are preferentially active during the dark. It doesn't mean that they won't sleep in the dark. It just means the majority of their activity takes place in the absence of light. We also know that acute pulses of light, so turning a light on, for example, in the middle of the night, will induce sleep in these animals. And we know that this is done through melanopsin phototransduction, so through these cells. But we also know that light exposure can exert a sustained effect. So it's not just these single small pulses of light, but also the exposure over time, which will affect the behavior of the animal. So this was back in 2009, this data was initially published that showed what would happen if you remove the melanopsin protein from the animals, so rendering these cells in the retina inert. And what we see here are images from the suprachiasmatic nucleus of mice with and without melanopsin retinal ganglion cells. And we see in mice, these OPN4 that there is a reduction in the amount of cells which are activated by a light pulse. And when we look then at the sleep in these animals, we see that in fact these mice here in the light period where they're more likely to sleep versus the dark period, in the black here, the melanopsin knockout mice, they are sleeping around 1 hour less during the light period, which is not recovered during the dark period. So there is a sustained reduction in sleep driven by the lack of this protein in the retina. So what pathways might be responsible? Both the previous speakers discussed the hypothalamus. Our current framework for a night active or nocturnal species is to look at this, for example, the ventrolateral preoptic area, which we know is very important for sleep induction, that this flip-flop model kind of exists, where as you have increase on the pressure to sleep, you have a decrease on the pressure to stay awake, and vice versa. We know through the OPN4 cells that these go through the SCN. We can see this on the anatomy. So we know that there is a direct innervation from the retinal hypothalamic tract into these brain areas, also to the end. But we don't really know how this feedback loop works. So how might it work? Does the SCN relay these effects as a secondary function? So it seems pretty clear, yes, but to look for experimental evidence, we kind of have to find a way to dissect this. Is the melanopsin-based photic input significant enough or sufficient to drive this sleep-wake cycle? So if you remove the circadian rhythm, will the animal still sleep? We know, for example, Virginie showed the data from the cave experiment. This is where you remove the light influence, and then you see the circadian influence still shows the persistence of a clock that kind of organizes sleep-waking behavior, even though it is free running. But then finally, can we separate then this circadian and direct influence of light? So what we did is we took mice. On the top here, we have mice similar to the ones I just showed you, so lacking melanopsin, and then normal mice. And in the bottom, we have mice where we removed the suprachiasmatic nucleus. So we removed the circadian function, as well as this pathway for the melanopsin information. And then we moved the melanopsin in addition to removing the SCN. And what we found is when we subtracted the amount of non-REM sleep or sleep between the light and dark periods, we saw this progressive decrease depending on what was removed. And the most interesting finding, for example, so again, confirmed that they slept 1 hour less, but that the mice without a circadian rhythm still sleep longer during the light period. So this is a proof of the fact that there is this direct effect of light, which is promoting sleep, regardless of a functioning clock. But once you remove both of these things, the animals become arrhythmic, meaning that they sleep the same amount during the light and dark period, and they are awake the same amount, as though there's no light going into the brain to change behavior. So what can we do with information like this? So what we did is we took this information and we tried to find a model representation of what all of these differences might mean. This is not so important, but what it does is it allows us to come up with this framework where we identify that the circadian rhythm by itself, under this normal light-dark exposure, is responsible for about 55% of the sleep-wake period behavior, whereas these sustained direct effects of light, so the exposure over 12 hours of light and darkness, that this is around 45%. Now, these are general numbers. This does not mean that it would work in every scenario or that it would even be translatable to other species. But the next thing we wanted to do is see, can we use these numbers, very simple 55 and 45%, and shorten the photo period? So to run an experiment that would mimic winter light exposure in northern and southern extreme latitudes. So we shorten the period to 8 hours a day, and what we find is that just using these two numbers, we're able to more or less model it doesn't account for all changes, but more or less model the amount of sleep. And there we see that it's fairly good at adjusting for this reduced amount of light exposure. So, but one thing we wanted to do is maybe come up with something a bit more complicated and a bit more maybe important. Now, everybody probably has experienced jet lag to different levels. Of course, I know that Virginie and Renske both lived, or Renske still lives in California. They're both from Europe. I came from California. I now live in Europe. I've certainly been on the plane many times with these 9-hour jet lags or longer. The basic idea with the jet lag is that you end up with two clocks that are out of sync. And we know that this causes disturbed sleep. We know that it causes daytime fatigue, difficulty concentrating, and mood changes as well. So can you jet lag a mouse? Now, short of putting them on an airplane with suitcases and making them wait in security, maybe we don't have the same stress level with the mice as with human beings. But what we can do is we can shift their photo period. So we can substitute or kind of simulate an 8-hour westward jet lag just by shifting the start of the light period. And what this gives us here on the bottom, you can see some actimetry from one animal, similar to what Renske showed in humans with the ActoWatch. We see that when the jet lag occurs, we start seeing this kind of shifting that occurs, and then after a few days, it seems to realign to this new photo period. So how do we apply the model to something like this? So we did some calculations, some fitting, and we found that a 2.2-hour shift per day could be applied to the circadian effect, meaning that there was this sine wave that was moving and it was kind of shifting a little bit every day. And what this gave us here under our baseline, we see our prediction versus our circadian and sustained direct effect model. What we saw is that if we slowly move the circadian curve, for lack of a better word, after about 4 or 5 days, it starts synchronizing. So this is how the model looks. Now, again, it's hard to fit this directly to animal behavior. There were 8 mice in this experiment, but it more or less kind of fits over the idea. So, and when you look at broader kind of light dark differences rather than these 3-hour blocks of time, we see that the model is fairly close given the variability in the data. So maybe the feeling and the resetting after jet lag, and this is not only a combination of a circadian effect, but is also a light exposure effect. And we certainly know that this is told to us to get light exposure at the right time. And this also helps with our eating behavior and things like this. So just to summarize briefly, in these nocturnal animals and the mice, so light influences sleep not only through the circadian timing, but also through this direct effect. I call it a non-circadian response. I'm not trying to be provocative, just to say that it's something that seems to persist outside of the circadian rhythm. And that even in the absence of the SCN, light will modulate sleep. Although an intact circadian system is necessary to have this rhythmic behavior or the sustained sleep-wake behavior. But understanding these effects may help us to predict how people react under these irregular lighting conditions, especially if they're shifting back and forth very quickly, either through travel or through shift work, you know. So now the last few slides I wanted to focus on are in the diurnal rodents. So I had the opportunity during my PhD to work in the Department of Integrated and Cellular Neurosciences. It's actually where I met Virginie when she was a master's student there. And we had this animal called the Arvicanthus ansorgi. So the Arvicanthus ansorgi has a more general name, the Sudanian grass rat. However, these are from Mali. So they were captured about 20 years ago by researchers in the department, and they have at this point been bred for more than 20 years in captivity. But let's say 10 years ago, when I was using them, 12 years ago, they were a bit more wild. But they're fairly small. They're not quite the size of a full rat. So they're certainly much bigger than a mouse, but they're very nice. You can see they have this nice fur. And they've been used in a lot of chronobiology studies, especially to look at seasonal reproduction, also to look at retinal function, and how they, as a diurnal animal, how they discriminate with non-visual function in different light intensities. But what I was interested in as a sleep researcher was what did it look like, their sleep and waking behavior. So along with people in the lab, we recorded them for the sleep and wake behavior. And the first thing you might notice in blue here, we see the wake, we see a lot of activity that occurs between these light and dark transitions. So that has this crepuscular behavior. Now this makes sense, the sunrise and sunset periods in the wild, that this animal, which is much less adapted to a laboratory compared to a mouse, which has been bred for 90 years in a laboratory. But we also see that there is more sleep that occurs during the dark period. So the first thing we wanted to do, focusing on light, is what happens if we remove the light. So you remove the light, it has still this strong crepuscular rhythm, and it has still this, what looks like a non-REM increase, sleep increase during the subjective dark period, the second half of the night. However, if you actually look at these differences and these 12-hour differences, we see that there's quite a strong difference, reduction in the non-REM sleep when you remove the light. And the same is the case with waking, although to a lesser extent. So then what happens if you try to induce waking by light? So to turn on the light in the middle of the night, what happens to the animal? Well, what we saw is that if you turn the light on 3 hours after the light has been turned off in the laboratory, we see this induction of waking that starts around 5 to 10 minutes into the hour and is sustained over the hour, but then takes a bit of time to go back down. This was also paralleled in high-frequency brain activity that we normally associate with exploratory behavior, cognitive processing, as much as these animals have. And what was interesting then, if we look at this same brain activity under these sustained conditions, what we see is, well, there is always this strong activity at these light-dark transitions and dark-to-light transitions, which is reflected but during the subjective light period of the constant darkness, so when light normally would be, we do not see this high-frequency brain activity, whereas we do see it when the animal is exposed to light. So this seems to then imply again that there is some light exposure-dependent behavior. So what if we did this back and forth. Every hour we change either light or dark, light or dark. So interestingly, what happened is we see that there's an induction in waking activity. So when the brain is more active, although it is a bit delayed. However, it is fairly opposite to what we would see in a mouse, whereas in a mouse, we see this induction of waking by a dark pulse. So I would say it's a good diurnal model. It is not a model for human beings directly, but neither are mice models for human beings. You know, they have less consolidated sleep than human beings do, but it does show that there is an increased wake behavior in response to light. You see that there is this light-dependent activity, increase in activity in the brain. And it sustainably increases wakefulness even during times of the day when they normally would be asleep. And then finally, that the temporal niche probably dictates the function of the environmental light. So just to summarize quickly what I was speaking about today, we have a lot of artificial light exposure. As Renske mentioned, as Virginie mentioned, you know, there is a lot of light that we're getting at weird times. We know that this probably contributes to insomnia and early arousals in certain cases, of course, with jet lag and shift work fatigue, you know, where light cycles are being changed constantly, and also to mood disorders and what we could say is cognitive fog, you know, some kind of fogginess. But in conclusion, I would like to say light regulates sleep and waking not only through a circadian clock, but also through this acute and sustained effect, which seems to operate in parallel to the circadian rhythm. The neurobiological rhythm mechanisms are fairly clear. This seems to be very strongly regulated by melanopsin. There are species-specific responses, which we always need to keep in mind. And there is variability. These are laboratory animals, so there's a lot of variability in the wild as well. But finally, research from these animals can kind of help us identify what this direct impact of light has on behavior and lead to more general ideas, hopefully, about how we interact with light as human beings and how this may affect healthcare and other outcomes. So I want to thank again the organizers and of course my colleagues at the University of Strasbourg and the University of Lausanne. And I'll be happy to answer any questions.
Thank you very much. Okay, thank you both for your very interesting talk. And now we'll take some questions. So if you have more questions, go to the Q&R and put them there, and I'll try to take one after the other one. So first question, I guess the first one might be for Renske. How do you explain that afternoon light is apparently less damaging, if it is, if following a good take of morning light?
I think that's a really good question. I think it's difficult because I think when we talk about light, you cannot just talk about a pulse as an independent event, right? Like from the moment we wake up, we get a certain amount of light, and this continues on until we go to bed. And I think the influence that light has on us is going to be dependent on prior light history, as we call it. So if I go outdoors in the morning because I have to walk my dog, I get a lot of lighting then. And then the effects of light in the evening, for example, are probably going to be a lot less intense had I not gone out all day and gotten any outdoor light exposure, for example. So I think it's kind of important to look at light exposure as a sequential event. Yeah. Does that answer the question? I hope.
Yeah. And from Laetitia as well, if light pollution disrupts human sleep, how about the circadian rhythm of wild animals? What is the latest research on it?
Yeah, also excellent question. I think actually that the disruption on animals is way bigger than it is on humans. I mean, after all, If we talk about light exposure at night, so outdoor light exposure, of course, we sleep with curtains closed, we sleep with other tools. So there are ways that we shield ourselves from artificial light at night. I think for animals, much less so. And there's some really interesting work that's being done about light at night and the influence on migratory patterns, on bird and mate choice, and all these kind of things. And I think, yeah, the research is showing that it's really, really bad for all these ecosystems, actually, and that the effects are much bigger than for us humans, even. So it's very worrisome. Yeah.
Thank you. Another question from Annelies. Did the duration of sleep differ between the early and the late group?
Excellent question. And I didn't go in all the details of the experimental design. So we corrected all our models for sleep duration because, of course, it's easy to, or it's logical to assume that those that go to bed late sleep less because of obligations, work, children, maybe. But there weren't actually large differences between the groups. So people slept about equally long. And we corrected all our models for sleep duration. So the effect of timing of sleep on health was independent of how long people slept.
Okay. Considering the increased exposure to artificial lighting and the detrimental effects this has on our health, what could the long-term implication be for the evolution of the human race?
That's a difficult question to answer. I don't know. I don't know if we're at the point to make any recommendations or conclusions about that. I think, as long as we still try to get outdoor light exposure, as long as we still try to maintain, let's say, normal light exposure rhythms, I think we'll be okay as a human race, but this is highly speculative. Yeah.
So there is 3 questions that might be together. So can older people improve their sleep by moving to mid or low latitude areas with longer daylight hours?
I don't think that has been proven yet, but it's kind of what the data would suggest in a way. Yeah.
Okay, and as well, is there a difference if people spend some outdoors time is there a difference if people spend time outdoors active or sitting? And how much time and at what time those outdoors activities?
Right. So that's an excellent question. We're actually looking into that right now. It seems to suggest that the effects on sleep-wake consolidation are better if people are active. So if it's really an afternoon, let's say a stroll or a walk outside versus sitting on a bench. But we have not really tested this in a methodological way. So it's a little bit speculative. Yeah.
Another one thing, thank you for the wonderful session. And may I know whether spectral composition of light has any impact in altering the sleep quality?
Yeah, I think this is also one of the topics that has been explored a lot, where people talk about the blue light hazard, basically being exposed to light of the shorter wavelength region, because that is most active on the circadian slash melatonin system, let's say. I think the data right now is kind of showing that it's really any light of certain intensity, and it's true blue light is a little bit more potent, but I would say any light can have these effects on sleep and sleep quality, just as long as you get enough of it, or yeah.
Yeah. I'm trying to find a question for Jeff, and then we'll come back.
Yeah.
I'm trying to, I think.
Well, I agree that what I talked about is less applicable to people's daily lives. I would say about
maybe.
say about light exposure that there's even studies to show that red light, which is supposedly not modifying at a certain intensity, will even start to cause problems. Even in mice or in animals where we presume that they don't have the retinal structure to interpret the light. As these lights start getting broader in their frequency response, they start actually triggering circadian issues or things like this. So yeah, I think it's always the exposure level and not just the wavelength.
Yeah.
So what was the question? Sorry, Bash.
No, sorry, I just, so I continue. Sex differences in aging effects of sleep fragmentation and menopause. Any idea?
Excellent question. Something that at least in humans is really not that much known about. I think sleep-wake fragmentation is common in anybody who ages, and we do know that menopause has a big influence, and it's a big deterioration on sleep quality, but it's really emerging research. So at least in humans, we don't know so much about it yet. We kind of look at it as a whole, but maybe Jeff has an idea about the perspective in mice.
Mice menopause?
I don't know.
I mean,
guess
look,
aging, sex differences,
exactly,
I guess.
exactly. So we do have this problem in animal research in general that we tend to focus on young male mice. And the excuse is always, well, because they're so similar, so then we don't have to think about things like female hormones and, aging. But it is true that at least over time, in terms of what we see in male and female animals, that they age differently, that there is more fragmentation that occurs in female mice, even though they sleep a bit better when they're younger. But then as they get really old, male and I say 2 years old, a year and a half, that's a very old mouse, the sex differences tend to disappear. But part of the problem is we just don't have enough research on it because it introduces extra variables that researchers don't want to deal with. So
Yeah. Yeah, I think this is a very interesting push that is starting to happen, though. Like,
absolutely.
funding institutes and such are really pushing for us to include all genders and take sex-based differences into account. But the research is really lagging for now. Yeah, it takes time to catch up. Yeah,
Absolutely.
yeah.
Okay, so again, with different blue lights. So blue light is a key factor to consider when using virtual reality in the evening, especially right before sleep. In your opinion, to what extent can the negative effect of blue light be mitigated, such as through the use of a night protection or low blue light mode, or by scheduling virtual reality use earlier in the evening rather than immediately before bedtime?
Yeah, this might be slightly controversial, but I'm a firm believer that blue light blocking glasses are not going to save you. As I indicated before, I think it's really any light exposure, and I think the idea of having, let's say, night shift on your phone or blue light blocking glasses, and then you can do whatever you like is it's probably a little bit misleading. I think your safest bet in terms of light exposure and activation and postponing of melatonin, I guess, would be to schedule your virtual reality earlier in the evening.
And if I can maybe add another small question about it, if you spend more time outside during the day, I think the light in the evening has a little bit less impact than if you spend your day inside, right?
Correct. Yeah. I think this has not been like methodologically shown, let's say in a dose dependent manner, but I think this is, I would agree with that. I do think if you get a lot more light during the day, you're a little bit more resilient to light in the evening or at night. Yeah.
Sorry. So I have a question about thanks for sharing the amazing results of better sleep and less fragmentation caused by daylight. Since the study is in larger group, would it be possible to translate this effect into financial benefits, like reduced health costs?
Yeah. That's a good question. I mean, I'm not an economist. I'm a biologist. I don't think about finances outside of my own finances, I guess. So I have not really considered this. I think it's hard to put a number on the health cost. I know there was an initiative from the Good Light Group actually to try and put a number to the benefits of getting better sleep. And I think they were successful in that. I think it's on the Good Light Group website actually. Yeah.
Exactly. So when we discuss how light affects sleep quality, is it more informative to look at cumulative light exposure across the entire day or at exposure during specific time windows, morning, afternoon, evening?
Yeah, it kind of depends because on the one hand, I do think you cannot look at light as a singular event, let's say the afternoon or the morning, independent of each other. At the same time, we do know based on the circadian system that light at different times of day has different effects. So I would say both, I guess. Like there's lots of research showing that light at certain times of day is more potent for example, phase shifting the circadian clock or changing circadian amplitude. So then it's more, it makes more sense to look at light at certain time blocks. But at the same time, as we kind of talked about, like, you're more resilient to light in the evening if you got more light during the day. So I would say the answer is both for humans at least. Yeah. I don't know how do you handle that with animals, Jeff?
Yeah, good question. I mean, with animals again, we try to control as much as we can. So because the more you can control the variables, the less you have to explain them after the fact. There was a big controversy, for example, at some point that we were using fluorescent lighting for all of our experiments, which, I'm sure most of the people, if not all of you, know the spectral composition of fluorescent lights has nothing to do with the biological construction of the retina. And it even flickers, and we don't even know if the animals perceive these flickers and things like this. And so, I mean, from my perspective, I think the best. Now I've forgotten exactly what is the original question because now I'm starting to think. What was the original question, Virginie?
Yeah, if I lost it. What is it?
I think if you should look at light exposure in blocks, let's say morning,
Yeah,
afternoon,
yeah,
evening, or
exactly.
sequential in a way.
Sequential, yeah. I mean, for us, it's very artificial, the whole thing, because we always keep this 12-hour, which would be a equatorial light dark cycle, I guess.
Yeah.
Also, it gets shifted depending on the researcher. Maybe they want to work earlier in the morning, so then they start shifting the animals. Or if they need to do experiments at night, they may even flip the light dark cycle, which supposedly doesn't have any long-term effects on the animal after about 3 weeks. But again, not really well discussed. With a rodent where the sleep and waking is kind of partitioned across the day, or even with larger animals, we tend not to think of morning and evening. We just think of light and dark periods, or if we want to do these very artificial light pulses, like I showed in the slide. So
It's very nice in animals. You can control anything. You cannot tell people to just sit in the dark for an it's just impossible. So it shows how the research in both areas is very complementary in that sense. It's very nice.
So for Jeffrey, with respect to the acute effect of light affecting people's sleep after time zone travel, would you prohibiting light at the endogenous night be enough to prevent the detrimental effects?
So jet lag recovery is a very controversial subject as well. So there's a lot of anecdotal evidence. There's limited empirical evidence as to how this works. And it also there's so many factors that go into play. I think one thing that really hurts is especially flying to the West. So flying to California, back to work, Renske. Flying back to work, that the exposure of light in the airplane is really bad. And not to mention the fact that people drink alcohol, they don't drink enough water, they don't move, the food is a bit iffy, So that really then you land maybe at 3 or 4 in the afternoon. You're completely exhausted because your circadian clock is at 5 in the morning. That you should probably be trying to expose yourself to light while you're on the plane to kind of start boosting this a bit. I think the main thing is with long jet lags, the first day is a wash because it's anyways not even a circadian issue at that point. It's just a fatigue issue. There's a lot of sleep pressure. You won't really start feeling the effects until the second or third day. And then, yeah, you should try to slowly expose yourself a bit. Early morning light exposure always works well. And yeah, not using your phone in a dark room, regardless of what color the light is coming out of it, is probably not a good thing. Going east is a bit trickier because it's so unnatural flying east that you even run the risk of flipping your cycle if you're not careful. So try to get light exposure, but I think it's also physical activity is very important. Light exposure by itself is not a panacea for solving all of our problems, as much as we would like it to be, So I think also going outside and having light exposure, even for a walk, trying to stabilize when you're eating, that you're not just eating whenever you're hungry. I think this really helps. So,
Yeah.
Okay, and staying a bit in the travel field, are there any studies on the sleep behavior of people who live far away from the equator, for example, in the north of Scandinavia, where there are extreme day-night cycle? And what was their sleeping behavior like before the invention of electric lights?
Yeah, that's a great question. There are some studies in these kinds of populations, and it's really interesting because they're not that different from people that don't live that far from the equator. And we think that there is some sort of genetic predisposition to this because they will tell you, like living in the dark for almost 24 hours a day, not everybody is resilient to that, right? Like seasonal affective disorder is a real disorder, which means depression in winter when there's decreasing daylight. And people at these kind of latitudes do not report that at all or very little. And we think there are some, genetic predispositions to be resilient to these kinds of things. And because otherwise it's impossible to live at these extremes. Yeah.
Okay. What can be said about morning person and night person? What are the differences in the brain process between the two?
I mean, that's a great question. We don't really know. I think when we talk about an evening person versus a morning person, we take it as an output of the circadian clock, such that an evening person tends to be, let's say, a later chronotype in which the circadian clock ticks a little bit slower, whereas a morning person would be somebody for whom the circadian clock ticks a little bit faster. I think it's really an endogenous preference. Like you like to be a morning person, you like to be an evening person. And yeah, you can amend that a little bit with light exposure, for example, but it will always be your endogenous preference. If it really, really correlates exactly to what happens in the SCN or what happens in the brain, I don't think we really know right now. That's my take on it, at least. Yeah.
And about that, regarding your first study about late people who go to bed late are more exposed to depression, did you check for chronotype? Because in my view, it would be that late chronotype wouldn't be affected so much, and that early chronotype that goes to bed late then would be affected a bit more.
Yeah, so there was a little bit more to the story than that I told, because our question was indeed, a lot of people have this kind of, let's say, desynchronization where they are an evening person, but they have to go to bed early because they need to go to work early, for example. So we were really interested to see if this kind of desynchrony is worse for physical and mental health outcomes. And the conclusion was that no, it's not the mismatch between what you like to be versus what you are. It's really the timing of behavior that drives mental and physical health disorders. Yeah.
Okay, I didn't know that.
Yeah.
And can you comment on the intensity of needed daytime light exposure, specifically indoor electric versus indoor daylight versus outdoor daylight?
Yeah, I am very resilient to make recommendations about lux in that kind of way. I think there are many factors to take into account. Light history, have you been outdoors? I think there are differences, inter-individual differences in light sensitivity. So I would be very hesitant to put a number on that. I think there are some recommendations for at least 250, I think, melanopic EDI, so light intensity specifically for the photoreceptor that translates most of the knowledge to the SDN. Um, yeah, so those are the scientific recommendations right now, I think. Yeah.
Okay. How do changes in the pupillary light reflex in children who are neurodiverse impact sleep regulation?
That's a great question. It's not quite my area of expertise. All that I know is that I think there is some emerging literature suggesting that children with neurodivergence are more light sensitive, and that this is one of the reasons why they're more prone to phase delays, why they like to go to bed or tend to go to bed later and have lots of sleeping problems. So it might be a light sensitivity thing, where probably reducing light intensity is the best way to approach it. But yeah, it's not my area of expertise at all. Yeah.
And would you advise for people with insomnia to absolutely avoid light during the night, or when they use stimulus control and get out of bed, could they watch TV if it's relaxing, so lowering stress versus avoiding light?
Yeah, this is a very complicated question because from a biological perspective, I would say try to avoid light as much as possible. But sleep is a very interesting phenomenon, at least in humans, where it's a combination of physiology and psychology. And your physiology can be at one point and at the right point for sleep, but the psychology is not there. And I think for some people, watching TV can be very relaxing and help get the psychology part, in the right mindset for sleep. So I think for insomnia, most importantly, I would say, yeah, what works for you. I think there is a balance between what we would recommend for the biology versus the psychology. So yeah, it's kind of a dodging answer.
It's always like this with insomnia, so
Yeah, it's very difficult. Yeah.
Yeah, it should be a balance between both, I guess. And, yeah.
Yes.
There's quite some literature that's not only the intensity but also the wavelength of the light is important. LEDs lack both in the cyan as the deep blue and UVA, UVB part of the spectrum. This impacts the OPSING 5 and IPRGC. Do you agree that the spectrum is relevant? And if yes, how should the ideal spectrum look like?
Uh,
Sorry.
I mean, we talked about it a little bit. I think yes, spectrum matters. I think light intensity probably matters more in a way. As long as you get enough of a certain light intensity, it will have an effect. Um, yeah, I don't know. Does Jeff have any ideas on this?
about what's
Passing it along.
the best light to design.
Yeah.
I mean, look, the information on opsin 5 also there's not so much research that's been done on opsin 5 to this point. UV spectrum also have to be very careful about what you include in light because it can be quite damaging to human retinas. To mice, it's a bit different. They have ultraviolet sensors, they're receptors, but then they don't see red light. So everything is a trade-off. But I would say what the ideal spectrum to look like, if you look at the sun, there is no difference between the amount of energy which is produced based on the frequency. So we're always trying to adapt this, but to say that one thing is more important, maybe we'll discover another photoreceptor in 10 years that is somewhere in between these other two, and then we realize all of our LEDs have nothing there. So, it's human beings are very adaptable and we always find ways to do it. So
How cool would that be, a new
New
photoreceptor?
photo, you never know.
Yeah.
Option 6.
Okay, so maybe because time is running, but our last questions. How do animals light researcher and human light researcher work together?
It's a good question. We try to do as much as we can. I think it's important to remember that translational research from animals to humans also goes the other direction. So it's a constant interaction from fundamental research to basic human to clinical research. You cannot just say we use animals to understand something in humans because maybe we'll discover something in the animals and then find something in humans or vice versa. So I think at least from my perspective, we try as best we can. Of course, as I said before, we have a lot of control over what we can do to modify the animal's behavior, to modify their genetic background, to modify their physiology, which you don't have in human beings. So, yeah, I don't know if you have what your feeling is on this, Renske, but
Yeah, I think I would completely agree. I think there can't really be one without the other. I do really think so. A lot of the ideas that we get for our translational or clinical implications really come from animal research, and similarly, a lot of the clinical, let's say, malfunctions can be replicated in animals because you have the control about genetics and yeah, I really think there can't be one without the other, and we try to collaborate as much as possible, but it can be challenging for many reasons. You become such a specialist in your own little niche. But I always read papers from the animal work, and yeah, I think we need each other for sure.
Okay, thank you both of you for answering all these questions and for your great talk. And thanks again for the organization to provide such amazing, deLIGHTed talk. Thank you for everyone who was there and asked questions. And I hope we see you very, very soon. So thank you very much.
thank you so much again for inviting us.
Thank you.